Hi everyone, I will be talking about the local resting and action potential in this video. I will start off with the resting membrane potential. When a cell is not stimulated, the stable, negatively charged electrical difference across its plasma membrane is known as the resting membrane potential. The plasma membrane contains a potassium channel and a sodium channel that uses ATP to move potassium ions into the intracellular space and sodium out of the intracellular space to the extracellular space. The plasma membrane intracellular value is negative 70 MV when it is at rest and prepared to transmit a signal, which is another name for being in a state of polarization. An electrical current is created when the resting membrane potential erupts due to stimulation from factors like light, changes in temperature, and pressure. Next, we have our local potential. The local potential occurs when the sodium gate opens as a result of a stimulus at the dendrite. The response starts at a dendrite, moves through the cell body, and descends the axon and terminates at the axon terminal. The example of a chemically stimulated neuron was used in the textbook. The chemical stimulus attach itself to receptors on the neuron, possibly representing a pain signal from a damaged tissue, which causes sodium to enter the intracellular fluid by opening the sodium channel. The voltage across the membrane decreases towards zero as a result of the positive sodium inflow, partially canceling the internal negative charge. Depolarization is the term used to describe any situation where the voltage changes to a less negative value. Like ripples spreading across a pond when you drop a stone into it, the wave of depolarization that is created when the incoming sodium diffuses for a brief distance along the inside of the plasma membrane spreads out from the point of stimulation. We refer to this short-range voltage change as a local potential. There are a few traits of local potential that were mentioned in the textbook. Because local potentials are graded, their magnitude varies based on how strong the stimulus is. And since local potentials are decremental, their strength decreases with distance from their source. And also, on top of that, because local potentials are reversible, the membrane voltage rapidly returns to its resting potential if stimulation stops due to diffusion out of the cell. Next, we have our action potential. The plasma membrane's voltage-gated ion channels can cause a more significant alteration known as an action potential. Only in situation with a sufficiently high density of voltage-gated channel does an action potential occur. A threshold of negative 55 MV, the threshold required to open the channel, must be reached by the local potential in order for the action potential to occur. Rapid depolarization results from the sodium channels opening as the sodium ions diffuse from the extracellular fluid to the intracellular fluid upon crossing the threshold. Following that, the intracellular fluid would pass through negative 55 MV, 0 MV, and end up with a positive 35 MV, which is the maximum action potential value. The membrane then repolarizes to its negative state when the sodium gate closes and the potassium channel fully open, allowing potassium ions to exit the intracellular fluid and enter the extracellular fluid. This occurs after the positive 35 MV has been reached. Once the positive 35 MV has been reached, the membrane will return to negative 70 MV. The potassium gates close, allowing the membrane to recover and be ready to do the action potential all over again. And that's it. That's a wrap of the video.